Okay, welcome back everyone to our Calculus 3 class notes. We're on page 60, section 14.5. And for functions of three variables, the gradient vector and directional derivatives, pretty much everything works the same. You just add the third component. So for a differentiable function, f of x, y, z, and a unit vector, u1i plus u2j plus u3k, in space, we have that the gradient of f is f sub x I, right? Partial of f with respect to x in the I direction plus partial of f with respect to y in the j direction. And then we have the third component now, which is partial of f with respect to z in the k direction. Similarly, the directional derivative, the derivative of f in the direction of u, is still gradient of f dotted with u. So it's f sub x u1 plus f sub y u2 plus f sub z u3. The directional derivative can once again be written in the following form. It's the dot product, of course, so we can write it as the length of the first vector, which is the gradient of f, times the length of the second vector, which is u. And that's a unit vector, so its length is 1. So we just get the gradient of f, the magnitude of the gradient of f times the cosine of theta. So the same properties listed earlier for functions of two variables extend to three variables. In other words, the f increases most rapidly in the direction of the gradient, and it decreases most rapidly in the opposite of the direction of the gradient. And there is no change where this derivative is 0, which is where cosine of theta is equal to 0, so the gradient and u are in the same exact direction. Okay, so example 55, let's consider f of x, y, z equals x cubed minus x, y squared minus z. So we want to find the derivative of f at the point 1, 1, 0. In the direction of v, which is 2i minus 3j plus 6k. And then we want to talk about these properties. In what directions does f change most rapidly at p0, and what are the rates of change in these directions? Okay, so for part A, we first have to make sure that we're taking our derivative in the direction of a unit vector. So v is not a unit vector, so I need to divide it by its length. And so the unit vector that we're looking to take the derivative in that direction is 2/7 minus 3/7 and 6/7. Take the partial of f with respect to x, y, and z. So partial of f with respect to x is 3x squared minus y squared. Partial of f with respect to y is minus 2xy, and partial of f with respect to z is minus 1. Evaluate all of these at the point 1, 1, 0. Okay, so f sub x at 1, 1, 0 is 2, f sub y is minus 2, and f sub z is minus 1. So the gradient of f at the point 1, 1, 0 is 2 minus 2 minus 1. Thus, the derivative of f in the direction of u is the dot product of these two vectors. So 2 minus 1 dotted with 2/7 minus 3/7, 6/7. And after simplification, that is 4/7. So the slope of the tangent line to the surface, f of x, y, z, equals a constant, right? It's some constant because this would have to be the level surface of a function of four variables if we wanted to visualize it that way. Or this is a function of three variables, which if that is some kind of hypersurface in 4 dimensions, which we can't visualize. But f increases most rapidly in the direction of the gradient of f, which is 2 minus 2 minus 1. And it decreases most rapidly in the direction of minus the gradient of f, minus 2, 2, 1. The rates of change in these directions are respectively the gradient of f, like magnitude of the gradient of f, which is 3, and the opposite of the magnitude of the gradient of f, which is minus 3.